Hi there, I'm just going to go through some more details on power screws. Some of it will be a bit of a recap of what we looked at last time, but we'll go this time obviously into more detail about calculating torque required to move a load up or down and so on. So let's get into it. Okay, so as we discussed before, power screws used for providing linear motion, hopefully in a smooth, uniform manner. With sliding friction, whereas for ball screws we had rolling action, so less friction. But in this video we're going to look at power screws. Linear actuators that transform rotary motion into linear motion. So that's just a recap of what we did last time. And also power screws used for the following reasons and others, but mainly to obtain high mechanical advantage in order to move large loads with minimum effort, for example, screw jack, to generate large forces, for example, a clamp or a vise, or to obtain precise axial movements, for example, in a machine tool lead screw. So we'll have a look at, got some pictures of that coming up shortly, I think. All right, so just a reminder about the efficiencies, between 30 and 70% with conventional power screws, and we can improve that by using ball screws that have rolling friction rather than sliding friction, up to and even above 90% for ball screws. So three main types that we discussed previously: square, acme or trapezoidal, and buttress. Again, have advantages and disadvantages in terms of efficiencies and torques and how easy or difficult they are to machine. Just a reminder of what the different shapes look like. So they operate on the classical principle of the screw thread and its mating nut. So if we have a screw supported in bearings and rotated while the nut is restrained, so many of you would have used something like this to raise and lower your car to change a tyre. So if we put a torque over here on this right hand side, that rotates the screw, and then in here we've got a nut, and one end is just a bearing. Yeah, so as we wind the screw, the screw doesn't move, but the nut will travel along the screw, raising or lowering the load via the scissor mechanism here. Okay, so that's one way. The next way is if we have the nut as part of a machine, like we have in a lathe, for example, and we want to move this tool post along the length of the lathe. So we've got the lead screw here. Inside the carriage there will be a nut, and as we rotate this lead screw, then this carriage will move along that lead screw. So a similar kind of action to what we have up here, but much more smooth and precise movement and location of the tool post. So if we have the nut supported, i.e. prevented from moving linearly while it's rotating, then the screw can be made to translate linearly. So the screw jack uses this, and we saw this in the previous video as well. So if we have the screw thread here, the nut is positioned here, can't move up or down, and as we rotate the nut, then the screw thread will move up or down to raise or lower the load. And of course, one of our design requirements would be that once we take this torque off the nut here, that the load doesn't just fall down. Okay, so you might be able to see it's a little bit small, but the thread here, the angle of the thread is quite low, just to make sure that there's no possible way that this that the load can self-lower. But we'll look at the equations for that as we go on. All right, So main parameters are listed there for you. Again, I'm just not going to read through and explain all of those. You can read those for yourself. And then we've got some fairly common and familiar equations for the just calculating the area from diameters, and then the stress, the nominal tensile stress or compressive stress, and the shear stress on the threads, and so on. Okay, we have tables of preferred dimensions for Acme screw threads, and again, they're just for reference, so we can, when we do our problems, we'll need to look back and make use of these. So this is all in inches. And then also this is the same table as I just shown you, but just split up into two so that it's a bit easier to read. I don't think there's any extra information. No, it's all the same information. Okay, so that's those tables that we need to look up to do our calculations. Just a reminder about metric power screws use a trapezoidal thread similar to the Acme thread, with slightly different dimensions, just so it's in metric. Yeah, it's characteristics similar to an Acme thread. And we've got the details of the different sizes of threads and screw threads for that metric trapezoidal screw. All right. So to study the mechanics of power screw, we need to consider two cases. One, raising the load, and secondly, lowering the load. And I've got in this diagram just some of the terms that we'll be making use of. So for example, the lead angle, okay, is the angle of the thread. Sorry about the dinging. That's Microsoft Teams telling me that there's someone telling me something. And then the lead here is the amount by which the screw or the nut would move in one rotation. Okay, and then we've got pitch diameter and so on. So we need to refer back to these also in our calculations and in considering our design for power screws. So if we consider the forces that are acting on the load, so basically what we're considering is that the load has to be moved up the thread. Okay, so we've got a force here needing to move the load up the thread. So acting vertically downwards is the actual load to be moved. We've got friction being developed between the load and the screw thread, and we've also got a normal reaction force. Okay, and again we've got our parameters that define the thread itself. So the lead angle, the lead pitch diameter, and so on. Okay, so if we consider the equilibrium of these forces, so this is going back to Introduction to Mechanical Engineering. I would have done something, or if you had me for Introduction to Mechanical Engineering, I would have gone through some problems like this. If you didn't do it in Introduction to Mechanical Engineering, then you probably did it in Fundamentals of Mechanical Engineering or Applied Mechanics and Design A. But anyway, so this is the free body, well, it's not quite a free body diagram because we've got the screw thread shown underneath. For it to be a free body diagram, we should remove that screw thread. But anyway, we're considering the forces that are acting on the load. So if we consider some of the forces in the horizontal direction to the right as positive equals 0, we can write our equation of equilibrium. So we've got the force P here trying to push the load up the screw thread. We've got the force of friction and its component in the horizontal direction. And we've got the normal reaction force and its component in the vertical direction. Sorry, not in the vertical direction, in the horizontal direction. Okay, because we're summing forces in the horizontal direction here. All right, so that's that. Now if we consider the forces in the vertical direction, so we've got the load acting downwards plus the friction force acting against the direction of motion. So we're trying to push it up, so the friction force acts against that. So that's acting downwards. So the component of that is positive because I've taken downwards as positive, and the vertical component of the normal reaction force. Okay, so then if we consider friction at the point of slipping, then we will have the familiar friction equation. Friction force is equal to the coefficient of friction times the normal reaction force. Okay, so if we take those, rearrange them, do a bit of algebra, we get these expressions here, and then if we look at the torque, so the torque is the force times the radius, and we can substitute in a little bit more. So we get the torque that's required to raise the load is given by this. So that's our load that we're trying to lift, the pitch diameter of the screw thread, the coefficient of friction, and the lead of the thread. Okay, so that's how we work out the torque required to raise the load. So this is with a square thread, so we need to know what the torque that we need to apply to the nut to raise the thread. So I think that's just a repeat of what we've got here. Yep. All right. All right. So I don't think we need to go talk about that much anymore. Just a reminder about what the lead is. Okay. So now we need to consider lowering the load. Okay. So now we want to push the load down the thread. Okay. So same as before. Consider equilibrium forces. This time we've taken the positive to the left for our horizontal forces. So we've got P minus the horizontal component of the friction force plus the horizontal component of the normal reaction force. And some of the forces in the vertical direction, again taking downwards as positive. We've got the load that need to move minus the component of the friction force and the component of the normal reaction force. And again, at the point of slipping, the friction force is equal to coefficient of friction times the normal reaction force. Do some more algebra, and we get the torque required to lower the load. Okay, and that's just repeated over there. And then an alternative version of this equation if you keep the lead angle in the equation. Right, note these are for a square thread. Now, we want, well, in many cases, we want the thread to be, or the screw thread to be self-locking. So, for example, the screw jack, if we raise the load, we don't want to have that just fall back down again if we take the torque off the nut that we've used to raise it up. Okay, so if we have a high lead angle, then the friction may not be sufficient to overcome the tendency for it to slide back down again. Okay, so we need to design against that. Right? Okay, and as I showed in the picture, the lead angle is rather small, so if you keep that low, then you're more likely to have self-locking. Right? Obviously, you need to do the calculations to make sure. Okay, so the friction force must be greater than or equal to tan of the lead angle. And you may remember a similar relationship for if you have a block sitting on an inclined plane. As you raise that inclined plane, when does the block start sliding? At the point where friction is, or the coefficient of friction is equal to the tan of the angle. Okay, so we can look at the efficiency of a power screw. So E can be expressed as the work output over the work input. so force times distance, etc. Another way to think about the efficiency of the power screw is to think about it as what's the torque required to move the load without friction over the torque required to move the load with friction. Okay, so we just use that equation that we came up with before and put the coefficient of friction equal to 0, and that gives us an expression for the efficiency of the power screw. Okay, so just if we have a different type of thread, so in this case just the Acme thread, there's a variation to the equation. So for a square thread, the normal force to that square thread is the actual load, whereas in a trapezoidal or Acme thread, the force normal to that surface is at a different angle to the actual load force. Okay, so we just need to modify the equation for that, and this is what we come up with. So these are from the Mott design textbook. Okay, and then finally the power required to drive a power screw, a familiar equation that we've seen before, power equals T omega. So if the torque required to rotate the screw is applied at a constant rotational speed, then the power is torque times omega. Okay, so I'm going to end the video there. In the tutorials, we'll go through some example problems. All right, that's it for now. See you next time. Bye.